The solar system is delicious.
The particles sticking together are microscopic at this point, far smaller than the melting sugar crystals. And as cotton candy illustrates how these solids accrete in the solar system, another amusement park attraction shows what makes them grow. Bumper cars wouldn't be much fun without collisions. And in the solar system, without collisions, there would be no growth, no accretion.
The accretion collisions that were happening in the early solar system are of the kind that allow objects to stick together through various kinds of essentially friction-type processes where you have things getting stuck together just due to mechanical interaction.
In the inner solar system, the process is time-consuming as tiny cosmic dust balls form slowly, stuck together only by random collisions in their orbits around the early sun. But in the outer solar system, the story is dramatically different. The giant planets are about to burst into existence in a cosmic blink of an eye. Beginning as a cloud of gas and dust, the making of our solar system will take 700 million years. Now, just 2 million years after its birth, the young system takes its first steps in creating a family of planets that one day will be as diverse as Jupiter, Saturn, or the Earth. For now, though, they are chunks of matter continuing their roller coaster ride in the turbulence of the solar nebula. The thick, rotating disk, made mostly of hydrogen gas, is embedded with solids. The inner zone is filled with small chunks of rock, but outside the boundary known as the snow line, there are also ices of methane, ammonia, and water, which dominate the outer disk. And for good reason.
They're all hydrogen compounds of one form or another. And hydrogen is the most abundant element in that region of the solar system at that point. That abundant hydrogen is combining with elements such as oxygen to form the water, or carbon to form the methane, or nitrogen to form the ammonia, and giving us those compounds which are then freezing out.
Continual collisions amid the turbulence make tiny specks of dust and ice stick together through friction and static electricity until they're large enough for gravity to take over. Eventually, they become planetesimals.
Planetesimals were the original building blocks of our solar system. They're incredibly small, only about half a mile to a mile across, but there were countless numbers in the early solar system. It was simply littered with them.
These half-mile planetesimals will eventually form full-scale planets, but of distinctly different sizes. That's what Ryan Chan of San Mateo, California, wanted to ask the universe by writing, why are the planets closer to the sun smaller than the giant planets farther away from the sun?
Ryan, the inner planets are smaller than the outer planets because the inner planets didn't have much material from which to be made, just metals and rocks and things like that. The outer planets, after forming an Earth-like core, were able to attract ices of water, ammonia, methane, and carbon dioxide. That made them get bigger. And then they gravitationally attracted gases, becoming much, much bigger.
"3 million years after time zero, planetesimals are merging into bigger objects called planet embryos, or protoplanets.
Protoplanets are built up of planetesimals, so they're larger, about the size of our moon.
Just beyond the snow line, where ice is most abundant, the teeming mob of protoplanets collide and fuse in a frenzy of planet building. Within just 3 million years, these collisions give birth to a frozen young planet, destined to become the monster of the solar system, the infant Jupiter.
Before it became a giant planet, Jupiter was sort of like a super Earth, maybe 10 or 15 Earth masses.
The early Jupiter is made of rock and ice and continues to grow. At a crucial moment, one last protoplanet slams into its surface. It's another roller coaster-like tipping point in the making of the solar system. The added mass sends Jupiter over the edge to become a gravitational bully.
After it reached a certain critical mass, Jupiter's gravity was able to very quickly draw in material, sort of a runaway effect that made it very large, very fast.
Like a cosmic vacuum cleaner, Jupiter sweeps up virtually all the gas in its orbital path, growing to 90% of its present size in just 100,000 years. Saturn, Neptune, and Uranus, in turn, follow Jupiter in devouring enough gas to become gas giants. The dramatic sweep of one or more planets clearing a lane through a disk around a star is thought to be common in the universe, a fact borne out in recent telescope discoveries.
We see this process happening in other solar systems being formed as well. We're finally at the point where we can image other disks around stars and the gaps that are being created by the large planets that are orbiting them.
In early 2011, astronomers using the Subaru telescope in Hawaii released a photograph of a star 450 light-years from Earth. An advanced optical mask allowed them to block out the light of the star itself, revealing the first direct image of a disk with zones cleared out by orbiting planets.
That's a really amazing high-resolution image that shows a disk of gas and dust around a star, and the inner parts have been carved out by one or more planets that have accreted material and also flung other material away.
3 million years along the timeline, Jupiter and Saturn are now the titans of the solar system. The two giant planets will eventually contain 92% of all the non-solar mass in the entire system. 10 million years into its life, the young solar system is virtually out of gas. In this case, the gas is the hydrogen and helium that fueled Jupiter and Saturn's swift growth.
The forming star had this huge solar wind that was clearing material out of the solar system. Jupiter and Saturn were fortunate enough to pick up most of this material in their orbits, which is why they're so large. Uranus and Neptune were a bit later to the game and were unable to pick up as much material, which is why they're smaller than Jupiter and Saturn.
During the time before the dust and gas were blown away, the forming solar system was largely hidden from the rest of the universe. Even as dust and gas were forming planets, the disk remained thick enough to block light from the protosun at the center.
At a distance of several Earth distances from the sun, for example, looking back towards the sun, in the earliest phases of the solar system, we wouldn't be able to see the sun. We wouldn't be able to see the visible light.
What would the early solar system have looked like to alien astronomers gazing at us from even greater distances? The Hubble Space Telescope shows us with photos of protoplanetary disks in a star-forming region 1,350 light-years from Earth.
We can see them at a variety of angles, tilts, relative to our line of sight. For example, if they're face-on, we can see a central star surrounded by a disk. But when we look at these objects edge-on, the gas and dust that is between our line of sight and the central star blocks the light of the star.
But now, 10 million years after the solar system began to form, with the dust and gas virtually gone, the sun-to-be shines brilliantly through space. It has yet to go through the process of becoming a true star, and at this point, it would seem strange to modern eyes.
The spectrum of light was very different, so it was putting out a lot of energy just as it does today, but it was actually much redder in its spectrum, so that early solar system would have been a very different color from what we see today.
The protostar, orange-yellow in appearance, is a seething cauldron,